for continuous time, this matrix by itself doesn't really mean very much because every epsilon in time it changes. It's not something I can really get a handle of. What I have to draw is coordinate system in which I look at the rates of expansion and rates of contraction per unit time. In other words, whenever I have an eigenvalue lambda, ith eigenvalue, it's natural to write it as exponential of time times a rate of expansion. The real part, and because this is a complex number, then we also put the complex part. Instead of looking at this complex number, I take its logarithm. And now I look in the complex stability exponents. So this will be called stability multiplier, big lambdas. These guys will be called stability exponents. So that's a rate per unit time, because there is time and this is dimensionless. So these are, maybe you wonder why I'm taking this logarithm. Basically, suppose that I have a system in which I have a constant rate of expansion. It doesn't depend on position. Then what happens to two trajectories, their distance will grow exponentially with time. And that's a totally natural thing to do. So here you have a different thing to plot. You should plot real part of lambda, which you use a lot, so we give it a name for every multiplier. Instead of I look stability exponent. If my multiplier is real, and there is 50% chance of that, then it doesn't have a complex part, and that means that it sits on this line. This is the imaginary part, call that omega. Now if it's positive, this is unstable. So what that means is if I have a neighbor which is on my eigenvector, corresponding eigenvalue some distance away, as the time goes they just shoot along on this eigenvector at the rate which is et to the mu. Or I could have a complex pairs, and because complex pair conjugate to each other, there's just minus of that. That's also unstable. This is the mu of I and this is the omega of I. Or I could have solutions that sit on this axis, they're purely imaginary. Multiplier is corresponding to the solutions e to the I omega. This thing is just rotating on a circle when I perturb it, or ellipse or something. It's not going anyplace, it's not going away. So this axis is where all the neutral marginal eigenvalues. Or they could sit, and for example in fluid dynamics, then there is an infinity of things like that. All of them are contracting because they're negative. Real part is negative, because here we have that absolute value of lambda, which is written as e to the time passed times the mu. Mu is negative, so they all contract. So for flows, you should do these things, and you have seen them in quantum mechanics, because when they teach you resonances, they do the same thing in quantum mechanics. It's not so unusual, but so for the maps, you care about multipliers. For the flows, you care about exponents. Stability multiplier, stability exponents.